Hi everybody, I'm Yuval from A21. And for the release of our new Jamba 1.5 family models, which are also open sourced, I've decided to go and revisit the white paper that introduced Jamba to the world, which is the hybrid Transformer-Mamba architecture, which is really the most novel thing about it. Okay, so throughout this video, what I'm going to do is essentially just go through that paper, make sure to really nitpick all the important things, and really provide you intuition and understanding about exactly what we did with Jump. So let's get started. Okay, and first of all, we're starting here with the abstract, where, like in every abstract, just presenting all the main points of the paper. Where here they're presenting the concept of Transformer-Mamba mixture of expert architecture. Okay, these are three different types of architectures, all combined to create Jamba, okay, which is short for Joint Attention and Mamba. And really, the thing about this paper, the thing about this architecture is that the main advantages here are really the output speed. Okay, the throughput is much higher than in regular transformer architecture. The memory requirements are much smaller, while we're still maintaining the quality of state of the art. Okay, so you can see here exactly flexible architecture, specific configuration, and then we can fit this model into a single 80 gigabyte GPU, okay, which is something which is really huge for the open source community. You can really do a lot of things with such a powerful model in very, very small amount of hardware, okay, like the A100 GPUs, 8 gigabytes, we have a lot of those, okay, and really here, this is like the main thing is that we made it in a large scale, okay, this is something you can actually take to production, high throughput, small memory footprint. Okay, and really the 256 token context length, this is something huge, and we will later see this is actually effective 256K. Okay, it's not just the physical ability of the model, it actually provides quality outputs as well with that. So let's start with the introduction, which is really just providing a background for all the things that are important to understand the architecture. Okay, so again, you can see that Jamba is a hybrid architecture, combines transformer layers, Mamba layers, and mixture of experts models. Okay, so essentially we need to kind of understand all three of them and what the upside and downside of each of them to understand why exactly we want to create a hybrid architecture. So let's get started with transformers, which I'm guessing lists all of you know in some cases, but the thing with transformers actually, what I want to talk about is the problems with transformers. Like they are the most powerful models for language processing. Okay, their quality is really top notch. It is the best, the state of the art. But the thing is that there is a problem with the time complexity and the memory, the space complexity, especially when you are working with long context. When I say long context, I even mean like 16K and above, not even like the 100K. And why is that? Okay, so what happens is that, right, when I have a transformer model, it uses inside layers that's called self-attention, where essentially, right, when we have a sentence, we want to predict the next token, right? So you can think about the metrics of self-attention when I have here, right, every token, and again, every token in here, in the word, in the sentence, and I have connections, like I have the relations between every two tokens in the metrics, in the input, which is really, really good in the sense that it has all the information, all the tokens really connect with each other and you have the full information. But the problem is, and this is why I draw the metrics, as you can see, in order to produce something like this, we're talking about quadratic complexity. Okay, so this is something that will take both a lot of time and also will require a lot of memory. Okay, so these are the issues with transformers. Okay, one is the throughput. Okay, throughput especially for long contexts. Okay, if I have a context which is long, it will take a lot of time for the response to come to all the processing to happen, and also the memory. Okay, it's not only about the parameters. Okay, memory is something that is comprised from many things, but like the total params are important, like the total amount of parameters in the model when you are doing serving, plus the KV cache, where the KV cache, key value cache, these are the attention, okay, the self-attention layers. this is something that you need to really save in the memory. We're not talking about RAM or like a disk memory here. This is something that needs to be in the cache on the GPU itself. Okay, and when you have transformers, the KV cache becomes huge. And this is something that will prevent us to really put everything in one GPU. So these are the setbacks of transformers. Okay, these are the issues that we want to tackle because, right, the quality is unmatched, but when you are going to production, when you are trying to really scale things, throughput and memory becoming more and more important. Okay, so now let's see what happened. Okay, and even before before we even go into Jamba, there are a lot of attempts to really come and solve that, and one of them is Mamba. Okay, and what is Mamba? Okay, so Mamba is something you can actually kind of see as either a development of RNN. Okay, a lot of things happened over there, or for SSM, which is state space models. RNN is a recurrent neural network. You can look at both of those things, but essentially, those are two types of architecture. The RNN is very, very old. It's something that's like more than 10 years ago. Didn't really catch up because training in RNN is something which was very, very hard. You cannot parallel the training, so it takes a lot of time. It's a network that has a recurrent feedback, so it's something that can handle sequences. And SSM, state space model, is something that comes from control theory, I think, where essentially you store everything in a space. So just to understand, just to really get a motivation or intuition of what is happening here, what are state space models, what is Mamba, essentially. If in Transformer I had a sentence where for every next token, I had the interaction with all the previous tokens that happened, now instead what happens is that in every layer I have a state. And this state keeps updating, okay? So it updates throughout based on all the tokens that I have so far. And now when I want to predict the next token, I just need to update the state instead of looking at all of the tokens that I had before. So what happens is that I'm really reducing the amount of parameters and especially reducing the amount of the KV cache. Because now I don't have to look at all the interactions at once. I can just update the space, okay? And essentially it's like either quantization or like remembering the important things. You can think about it like that, okay? Not actual quantization that happens in the model, like the idea of quantization, where essentially instead of every time when I want to process a new token, trying to predict a new token, instead of looking at everything that happened so far, which is what Transformer is doing, I'm looking at a state, a representation of something that happened, all the things that happened before, and this state keeps updating every time. Okay, every time that I'm feeding a new input, then it updates according to what happened before, and then based on that, I will predict the next token. And this is something that happens in every layer. Okay, so obviously this ability, this type of architectures, these are something that really makes the model more efficient time-wise. Okay, but the problem is the quality. Okay, and this is something that happens a lot, right? When we have a paper, you can either show that your new model, new architecture are superior in quality, or you're superior in other things like in time, okay, in throughput, and then you have to prove that you're matching the quality. And this was like the power of Mamba, okay? The creators of Mamba, what they did, this is a paper from 2023, by the way, okay, so not that long ago. What they did is really showing that in smaller scale models, Mamba architecture, which is either like, you can think about it as an evolution of RNN through linear RNN all the way to Mamba, or evolution of the SSM, the state space models. Okay, this is something that they really optimized in the level of the hardware even, to make everything more efficient and to make the architecture really stand out. And what they showed is they are comparable with transformer quality in models like in millions, maybe even up to 1 billion parameters model. But these are really like small models, right? So this that Mamba did, they released the new architecture, which is really, really good, really comparable with transformers, but still rather in the small scale, like the small language models. And this is something that for people to take to production, you really have to work on that. So, by the way, if you do want to learn more about that, I really recommend this video. I will put a link to it. It's something that really will provide good explanation on what is Mamba and exactly how it differs from transformers. And the last thing I want to talk about is what are mixture of experts. Okay, and here in mixture of experts, this is something that really is very, very popular, right, in the last year or so, from Mixtral models to Databricks to, I think, almost most of the models right now come to solve that. And this is because, right, when we talked about transformers, right, we had two problems that we talked about. Okay, so transformers, we had one, memory. This is what Mamba can solve. And the second thing is the inference time or latency. Right, when we said that for really long context, think 256K, you have to keep looking at all the interactions between all of them, okay, quadratic time. Where this is something that mixture of experts come to solve. So in theory, okay, like the really intuition of what is mixture of experts, you can think about the fact that you have like several models. Each of them is an expert in their field. And once you have an input, this input goes into some sort of router or a gated component that essentially says, well, this input should go to this expert, and so on, okay, in every layer. So this is like the intuition of mixture of experts, and what actually happens, okay, it's not that far from that, it's just not really that, is that every layer in a mixture of expert architecture, okay, the layer of mixture of experts looks something like this. Let's say I have 4 experts, and now, so there's still like the router, the gated component. Now the input of every token is assigned to one of those or 2 of those, depends really on what do you decide. And essentially what you're getting is that you have a very, very capable model. Okay, it's a big model, so it's still same memory as storing a regular model, but now the inference time is much shorter because every input will just go here and then let's say go through here and so on and so on. Okay, this is like they really introduced the concept of active parameters, where you can have the total amount of parameters or available amount of parameters in a model. In pure transformers, this is really what happens, right? Every token goes through the entire network. It has to go through all the parameters. Where when I have a mixture of experts, I only, in inference time, I really feed it forward only through some of the model, okay? Only through the experts. So I'm getting active parameters, which is much smaller than the total parameters. And really here, if you want to learn more about mixture of experts, I highly recommend this blog post from Hugging Face. I think it's really a masterpiece in explaining what is mixture of experts. Like really, you will get there when you actually like fully understand it. But what you really need to remember is that mixture of experts is a way to really train a model with a lot of parameters that on inference time, right, will feed forward through less of this amount and will be much more efficient. So when you kind of understand that, okay, this is why Jamba includes all of them. Okay, it includes both layers of a pure transformer. It includes layers of Mamba, right, because we do want it to be faster. And it also has MOE, mixture of experts layers, in order for the models to be really fast also in inference time. And really what we see here is that we do get this, this architecture that kind of enjoys all the worlds. Okay? And this is important to say, okay, both of the models, what we're seeing here, this is like the first version that we released on March. This was just the base model that was released on Hugging Face. You will see now that you have 2 new models, Jamba 1.5 large and 1.5 mini. okay, where mini is in this size, okay, 52 parameters total, 12 be active parameters, okay, the active parameters comes from the mixture experts element, okay, and you can see that you have both of these models on Hugging Face. So now what we want to do is to really delve into the model architecture. Okay, so let's just look at this image. I think it's kind of rather clear and really explain everything, where essentially this is how a Jamba block look like, okay? And really this is like the what is inside of the Jamba model, but you can kind of play with it as you will see later. You can see that it starts with a Mamba layer, then a Mamba MOE layer, Mamba, Mamba MOE again, Transformer, Mamba MOE, Mamba, and Mamba MOE. And now on the side, we can see all those layers. So how does the transformer layer look like? Well, we have our RMS norm attention, and then RMS norm and MLP, where the difference between the transformer layer and the attention MOE layer, right, is just essentially, it's this part, right, MLP and MOE. Okay, so essentially either one big MLP or we have an MOE, a mixture of experts layer over there. And it's the same really with the Mamba layer as well. So RMS norm, Mamba, RMS norm, and then either an MLP or an MOE. Really depends on the amount of MOE layers that we want to do. Okay, so what you see here, this is the actual thing that we will see. This is the actual layer, but the model architecture is actually something which you can really play with. Okay, you can really, if you want to build a Jamba model from scratch yourself, you can really play with all the parameters that you have in order to get what is optimized for your use case. Okay, so let's see what we have here. So again, combining Transformer, Mamba, MOE allows flexibility, balancing sometimes conflicting subjective of low memory usage, high throughput, and high quality, right? No free lunches in life. If you want high quality, you have to pay probably on throughput or on memory and so on, okay? You cannot really have it all the time. But here it seems that we strike a really, really good balance. Okay, so okay, again, there's like a comment here about the total size of parameter is misleading, right? Because in MOE, there is the number of active parameters, which is what really goes to the inference time, where we do also need to consider all the time the KV cache, right? We've spoken about it a little bit, and here you can see a table. Okay, so again, you can see when we go through Llama 2, Mistral, this is the 7B parameters, and Mixtral, this is the 8 times 7B parameters. You can see that even though the Jamba has 52 available parameters or total parameters, okay, this is still something that active parameter-wise, it's even less than Mixtral. And you can see really, right, those two, Llama 2 and Mistral, you can see that when those are equal, it essentially means that this is a fully, like no MOE layers at all. Okay, makes sense. Both of them are pure transformers. Mixtral is an MOE as well, so you can see from 46 to 12.9. But what's really interesting here is actually the KV cache. Okay, and really, this is for 256 context. You can see that for Llama 2, it's 128 gigabytes, just the KV cache to handle this type of context. For both of those Mistral, it's 32 giga. So even like if you wanted to put, if we will, right, drop all the activations cache that we need to do as well, just the Mistral here, the 46.7 plus 32, this is something which cannot fit in an 80 gigabyte GPU. So this is something that it's worth to remember all the time, that you have to look at the active parameters, and you also need to look at KV cache when you want to really analyze a model throughput-wise. So now let's continue. And really what we're seeing here is that essentially, right, this is like a general architecture, the Jamba models, and you can just play with it according to those parameters. So let's understand what we're seeing here. Okay, so we have L, the number of layers. Okay, essentially, this is something that is determined by the number of layers per Jamba block. Okay, so in this case, you can see 1, 2, 3, 4, 5, 8. Okay, so in this case, L equals 8 in a Jamba block, where in the actual architecture of Jamba, there are 4 Jamba blocks. So L is the number of layers in a Jamba block. Okay, A to M is the ratio to attention to Mamba layers. So, right, if attention is like 0, so this is pure Mamba. If the M is 0, this will be pure attention. And in this case, if you'll see 1 to 7, it means that for every attention block layer, there is 7 Mamba layers. And if we will go here, right, so we will see that okay, this is something that, sorry, we have 4 red Mamba layers and 3 green Mamba layers and only 1 transformer layer. So again, 1 to 7. So this is what this ratio means. E means how often to use MOE instead of a single MLP, which is something that will really make the model faster in MOE in the sense that, sorry, not faster, right? It will make the same inference time as if we're using a single MLP. The amount of parameters, the total parameters of the model will be larger, but the model will be much more capable. N is the total number of experts per layer. Again, this is something which is enlarging the amount of experts. And K is the number of top experts used per token. Okay, so it's really standard in most places to see K equals 2. If you remember when we talked about, we have this router and then all those experts. So we said that usually it routes it to 1 expert. So it's actually more, what is more commonly used is to use 2 or more, but usually it's 2 experts. So the feed forward happens throughout 2 experts. This is something that will add to the inference time using routing to 2 experts instead of 1, but it will make the model much more capable. Okay, so really you can see here that a lot of flexibility. If we increase M and decrease A, so the ratio of Mamba layers reduces the required memory, storing the key value cache, the KV cache. Right, this makes sense, right? We like the A provides us like the high quality of attention, the M provides us the low memory of Mamba. So really, what we want to do is balance. And you will see later that what we ran is a lot of ablations on smaller models before we went to train the big model. Okay, to reduce overall memory and so on, balancing N, K, and E affects the relationship between the active parameters, total available parameters. Okay, so larger N increases the model capacity, but more memory, right? If I have more parameters in the model, I am more capable, but I do need to store it in the memory. Large K increase the active parameter usage, like we said. Okay, this is something that really makes the model more capable, but short, like longer inference time. Okay, a larger E decreases the model capacity, decreasing both the compute and so on. You can see really here all those explanations. And I think the most interesting thing here is the fact that they said that they added RMS norm. Okay, this is really something that helps the model to train. Okay, remember in the original paper of Mamba, we're talking about up to like 1 billion parameters, which is amazing, right? The fact that they developed this architecture, but it doesn't hold when we talk about production. Okay, we really want to take this part, and really when you go and scale up models and you like want to add more parameters or really build it to be much capable for production, you really need normalization of some sort. Okay, the gradients are really exploding, all the activations, like everything there is a mess. And this is really what helped the RMS norm in the Mamba layers, as you can see here. Okay, so really, they said that also they did like a lot of testing and positioning and positional embeddings, positional encoding is not something that apparently really help for Mamba. So they're just like a lot of things that they noticed, and really, okay, they just played with all those parameters with like smaller scale, did some research, and then what they did is really chose the best architecture to really balance all of this. And this leads us to here, to reaping the benefits, where essentially, okay, it's not like we worked in a silo or a void, right? We are working in this industry. We do want builders to really build and people to really use those models to do things with that. And like the thing that really keeps us moving forward is the all the hardware considerations. And this was one of the main things. Okay, Jamba's implementation for a single 80 gigabit GPU. Okay, and this is something that was really, really important. This is really how we chose those parameters. Okay, so you can see here L equals 8 in the paper. Okay, in the actual model, we have 4 Jamba blocks where in every block we have 8 layers, like we've seen in the image. There is a 1:7 ratio attention to Mamba layers, where actually it's written somewhere here below. They've seen like in the ablations that 1:3 provided the same results in quality. They tested a lot of like 1 to something and so on, and they saw that 1:3 and 1:7 provides the same quality really, but 1:7, right, more Mamba, right? This represents the Mamba. So more Mamba models, more Mamba layers will give us less memory and faster inference time. Okay, so this is something that, that really the choice was because of that. Okay, even though they could choose 1, 2, 3. E equals Z, meaning every 2 layers using MOE, and not every layer or every 4 layers. 16 experts. Okay, so essentially, like every 2 layers using 16 experts, you can say it's kind of like E equals 1 and N equals 8, like using 8 experts every layer. So you can like think about Mamba as like 8 times something if you want. Okay, it's really the same effect, but better in hardware. And K equals 2, you only want to use 2 top experts for every token. Okay, which is something which is kind of standard. For the ablations they found that it really works better. Okay, so again, this ratio really chosen according to the ablations. And again, the configurations here was for the model to fit an 8 gigabyte GPU with those weights, okay, int 8. Well, really, okay, this is something that up to, I think, yes, we wrote it somewhere here, but up to 140K context window. Okay, so this is really amazing. Okay, like this is a lot and lots and lots of context you can use with this single GPU that you can really, right, you have like dozen for a buck or something. So this is something that is really, really good for builders, especially for those who are not working in large enterprises that have access to a lot of compute. Okay, so they talked about here all those balancing and so on. And now really want to see how good it is. So you can see here, for instance, like how content, okay, so I really went ahead of myself, so let's just go through the graph anyway. Okay, context-less feeding to a single 80 gigabyte GPU. You can see that we are, with the Jamba architecture, managing to squeeze 140K. This is a lot. This is like 4 books, I think, something like that. It's really like a lot of context, where in Mistral 8 times 7B, you can only fit like 64 on a single GPU, and with Llama 70B, less than 20. Okay, and it is important to say that, right, we successfully trained it to up to 1 million tokens. We released it with 256 tokens, both the new versions and the old version. Really, the main reason here is because of priorities. Okay, we managed to do that, but we saw that the industry is currently don't need most of the industry the 1 million tokens, but do need that 256K tokens. Okay, so this is something that we really focused on, and this is just like a priority thing, mostly. Over here, you can see the throughput analysis, okay, where we present here a lot of information. Okay, so you can see here several settings where we really made sure that we have all the hardware, same hardware for everything, like really setting the scene so the playground will be fair. And okay, you can see 8K context length, generating the output of 512 tokens. And here you can see this graph. Okay, Jamba allows processing of large batches, like 3-time increase in throughput. Okay, so you can see here that with Llama 2 13B, 70B, and Mixtral, these are the things that you can really put in a single GPU. So Llama 70B can only do 2 batches. You can see that Llama 2 13B can only do 4, Mixtral can only do 8, and we can put 16 batches of those type on a single A100 GPU. What you're seeing here on the right, this is the throughput analysis, okay, where you can see that we have on 4 GPUs throughput per tokens per second, where this is the input length, okay, the total context window from 1K to 128K. What you're seeing here is the total number of total tokens, okay, throughput of the input plus output tokens, so the encoding and the decoding. And really what happens here is because of Jamba's architecture, because of the fact that the processing time does not grow quadratically, it doesn't even, for the input decoding, it doesn't even grow linearly. It grows lower than linearly. You're seeing that for this measurement, we're really getting a lot better throughput than all the other models, which are all transformer, pure transformer. Even Mixtral, which is like with Mixtral experts, still all the layers here are transformer. And those really, the throughput, this is something that comes from the combining Mamba with transformer. Okay, this is what we're getting here. Regarding for training and infrastructure, okay, so nothing too major here. NVIDIA H100 GPU, in-house proprietary frameworks for data, and I can really say, as someone who works here and looking at all the algo teams, we really have like a bunch of the smartest people I've ever seen in the world. So really, they know what they're doing. So now let's go to evaluation. I do want to, for a second, just go to something that I think I missed about the throughput. Okay, here it is. So this is, I think, one of the main key sentences that we have here. Okay, so despite the fact that Jamba has not yet enjoyed optimization of the kind the community has developed for pure transformers, we still get those results. Okay, this is something that happened in the last 6 years. Okay, really, the last 6 years, all the community, the amazing community in Hugging Face, really added more and more optimizations, and you can really get good quantization, good results, good serving options through the community. And we do expect that, there's only a limit how much you can really stretch it, how much you can really squeeze that lemon. And here, this is just the beginning. This is the start of a new architecture that we're hoping to see all the community really come and really want to optimize that, especially when both of our models are now open source for everybody to use. So we really do expect it to be much better than what we're seeing here. Now let's talk a little bit about evaluation, where here, there's usually some types of standard evaluations where you do need to show some academic benchmarks. And also we kind of did a lot of doubling down on long context quality to really show that it's not only we can do those, process this long context in a fast way, but also we do it in a high quality. So we have the academic benchmarks, okay, nothing that is too surprising. The common sense benchmark, HelloSwap, Winograde, ARC Challenge, RKey, Pika, the reading comprehension, we have BolQ and Quack, the GSM for 8K, the math one, human eval, code, natural questions, closed book, and truthful QA. Okay, all those Q&A, both of these are question answers benchmarks, and MMLU, of course, and BBH. Right, and you can see here, really, these are the results of, again, this is the model that was released on March. What you will see now on the internet are the results of the new Jambas. We have 1.5 mini, which is the same architecture as this one, the same size, and large, which is the same architecture, but much bigger. You will see different results, okay? The models really improved, but you can see here, Llama 2 was out then, Jamba 1 was out only then. You will see us with other competitors as well. See, we're still getting really good results, okay? Really comparable results to all of these models. This is reasoning, comprehension, aggregated. And again, this is just the beginning. You will really see it now, if you will look at the new benchmarks, really highly improved, and we really do expect to see a lot of improvements throughout the community. Okay, so what we're seeing here, okay, we're like, may think to yourself, this is a 52 billion parameter model. How do you compare yourself to a 13B? But again, the active amount of active parameters is 12 billion parameters. So this is what we do expect from the model. Okay, this is like the ballpark of really the inference time and how much it costs. Okay, so these are like the regular benchmarks that we have. You can really see here also explanation about the KB cache and so on. It's actually, I think, more interesting to look at the long context evaluation. Again, this is something that will come more and more for the benefits of the additional Mamba, or the hybrid architecture. And this is something that the industry really looks right now, and really you see a lot of talk on long context. And this is interesting, at least in my eyes, and for those who wrote the paper here. Okay, so first of all, we have like the needle in the haystack, which, if you don't know, this is like a simple test where you have a lot of context and like a needle, like a sentence that in the middle of that, and it moves. And the question is about this sentence. Okay, so it started with like, where is the best place to eat a sandwich in San Francisco or something like that. And this is the question that they're asking. And you can see here, right, what you want to see is everything green. And you can see that this is a depth, meaning where the information is percentage-wise, like if it's in the beginning or the end and so on, and how large is the context window. And you can see this is like fairly good context, long context handling. Again, these results are much like more improved right now, and you will see updated benchmarks out there. And it's actually, I do want to talk about something which is like an extension of needle in the haystack, which did not make it on to this paper, but I think that is currently the most interesting benchmark for this kind of thing, which is ruler. Okay, essentially ruler expands on needle in haystack and says, what is the real context size of your long context language model? Okay, essentially, how effective is it? Okay, where there is the claim length and there's the effective length for every model. And you can see here, this is a paper by NVIDIA. You can see here the public GitHub. And this is really the paper where, sorry, they're really showing that, okay, there is like benchmarks for long context, and you see what is the average length, and is it synthetic or is it realistic data? And really, you can see here that ruler is like any average length, so you can really test all the context window, and this is synthetic. And they're really like showing all the tasks, right? So you can see here that you have a single needle in a haystack. So what is a special number? So this is just like a same thing as needle in a haystack. There's multiple keys, so you have several options to answer, multi-values. So now you have to answer from both places, not just one. Multi-queries. So now these are like different questions. Okay, so the model has to answer. Variable tracking, again, it has to really follow different places in the context in order to do that. Common words extraction, frequent word extraction from what are the three most frequently words appear in the context above. So this is something that really requires the model to do statistics on all the context. And question answering, really see that the model can answer question based on everywhere in the context and not just one. Okay, so this is something that really shows what is the effective context length. Okay, because context window is like a physical quality of the model, but really it has to do it effectively, not just getting that. And here you can see the effective context window. Again, this is not totally updated. We will have an updated version with more models that have been tested so far. But you can see that there's a lot of models that kind of around in the 32K and especially in the 64K are getting really low results. And this is something that, okay, we only tested it after the release of this white paper, but it's something that we really think is important, not just provide long context window physically, but also do it effectively in a good way. So this is something that you will see, the ruler benchmark. This is something that really helps everybody understand how good is the context window for a model. Okay, so you can see here also natural long context evaluation. Okay, so we use data and also in context learning, meaning few shot, where if the data itself is long and you're using few shot in the prompt, it only makes it longer. So you can see here for data sets, banking, NLU, TrackFind, and another one, clinic. Okay, and you can see here really throughout the number of samples, greedy, this means like sorry, with temperature 0, and you can see really like the match. And even though here, so in clinic 150 and NLU intent, Jamba and Mixtral are really the same. On banking and TrackFind, Jamba really passes Mixtral from where the amount of samples becomes quite large. So again, this is a long context thing where for longer contexts, okay, this type of architecture is really good. It's really fitting to handle those cases. Also, another thing we did here, okay, so question answering data sets. Okay, first, before it was classification, now it's question answering data sets from long inputs. Again, taking and do it in a few shot format. So first of all, it will be easier to enforce the output and also to make the context even longer. And you can see here again that Jamba really beats Mixtral in almost all of them, especially on the average. So this is better. And again, all these types of models, right? The pure transformer usually will be better than like pure Mamba on most of the tasks. But really, combining them and making them comparable and with higher quality while maintaining faster speed, okay, and better throughput, this is like the magic here. This is the main differentiator for those type of models. And now you can see here in section 6, there's like a lot of ablations and studies. So first of all, they're setting the scene here and really making sure different design choices show the benefit of combining both of them and so on. What do we want to do? What do we want to see? And some academic benchmark that they used for these ablations. So the benefits for combining them. So again, we did like for 1.3 billion parameters trained for 250 billion tokens. And you can see here the results of all of them. Like I said before, we did a lot of ablations. And you can see here the performance, where just attention and just Mamba perform worse on all of those. But these two for Jamba, without even an MOE, so 1 to 3 and 1 to 7, okay, these two settings really made the model better, okay, overall performance. And because the 1.3 ratio is more compute efficient, this is why they chose this one. Okay, so like we talked before, they did some ablations. They saw that, yeah, it works better. And since these two works roughly the same, no use on choosing the model that has more compute. Okay, and here you can see, okay, what is this? The attention-Mamba ratio, the training loss for them. Okay, so you can see that right, the blue and the purple are the same. You probably only see the blue, but the purple is there with it. So also better. Okay. And again, you can see here the vanilla transformer, vanilla Mamba, and attention-Mamba hybrid models, 7B. And again, you can see here that it works, right? Now the model is larger than what we had before, and really it provides more better results. So with this in mind, they went to really train everything. Again, you can see here the loss, and really here the purple really stands out. Now the question is maybe why this combination work? Why not go pure Mamba if all you want to do is to save on speed? And here you can see some really nice example where probably Mamba doesn't really work well on tasks that include few shot. Okay, and this is because, okay, if in transformers, right, we know that every new token really has connection to all the inputs. In Mamba, we have the state. And this is something that we really saw, I think specifically for the IMDb, where IMDb, for those of you who are not familiar, you have a lot of reviews there, and the choices to set to sentiment analysis is either positive or negative. Okay, and this is exactly what they're reading here. Okay, the attention model is very good to adhere this format. Okay, attention model, once you will give it the few shot, it will always say either positive or negative with really, really high probability. Where for the Mamba model, we had a deviation. It will say very good, very positive, funny, bad, poor, and all those kind of things. So to go pure Mamba is something that would have been like to lose all the advantages on pattern following and really adhering to a format that we are getting for pure transformers. So, okay, this is something that probably really doesn't work with in-context learning. So we really seen that just by adding some attention layers, we can still maintain that. Okay, and you can really see here something, a visualization, like an anecdote in the paper, to really see that, see here, negative, negative, positive, these are like the attention maps. It's just like a nice thing to see. And here they're suggesting maybe let's look at in-context learning in hybrid models in even larger scales and to see what happens there. How does it work? Like what exactly happens there? How does it look like so something that can be nice like for the academia. Adding the mixture experts. Okay, so they did a lot of experiments. And you can really see here that Jamba with no mixture expert or with mixture experts. Okay, so the performance is much better, which like it's something that makes a lot of sense, right? Mixture of experts essentially means add more parameters to the model. Okay, the overall amount of parameters of the model is larger. It's just that you only activate some of them in the inference time. So we can still maintain the same inference time. We are staying in memory, but we're getting a much more competent model. So here, so stabilizing Mamba at large scale. So here they're usually just mentioning what happened, how does it work, and really the norms. The RMS norm is something that was the main thing here. Okay, the gradients kept exploding, moving up, and so on. And the RMS norm really worked better. And they also found out that it doesn't really require positional information. Like it doesn't really affect on the work. Here you can see the loss with and without the RMS norm. It's really like nice to the eye. You can see this is something that is not stable. You cannot really train anything with that. And with the addition of the RMS norm, you can see it like the really nice movement here. And also, okay, positional encoding doesn't really affect a lot. So from here, the conclusion, right? So there is a neural architecture, attention, Mamba with MOE. And really, this is, I think, the future, probably, right? You can only go so far with pure transformer models. And here you can really get the best of all worlds. And really, I think the main concepts here to remember is the fact that we have the total parameter, the total params, we have the active params, and we have the KV cache, okay? Where this is something really, the total params, we always had it. The active params is something that was introduced with MOE. This is for the inference time. And the total params plus the KV cache really indicates the GPU we can serve on. Okay, so I think this is a really, really nice architecture. This is something that will probably here to stay for the long haul. Personally, I'm really excited about the release of the two new models, Jamba 1.5 large and Jamba 1.5 mini, and I really can't wait to see what the community will do.